It's our great pleasure to have Professor Alán ASPURU-GUZIK visit to our university. Alán is now a professor of chemistry and computer science at the University of Toronto. It's quite unique combination. Normally, you do physics, chemistry, or biology, chemistry, but very seldom computer science and chemistry. But that's why we're really gonna have enjoyable afternoon with Alán. He's a Canada 150 research chair in theoretical chemistry and the Canada CFA AI chair at the Vector Institute. So this is all, I believe, is a big initiative for the whole Canada. So Alán also holds this Google Industrial Research Chair in Quantum Computing. Is a director of this acceleration consortium. It's a University of Toronto-based strategic initiative that aims to gather researchers from industry, government, and academia around the pre-competitive research topic related to the lab in the future. I think that's more like with a great vision to push the technology all the way to the market, from 0 to 1 until to the last miles. Yeah, without further ado, let's welcome Alán to give us his nice lecture.
Thank you.
It's the IAS Distinguished Lecture Series. Okay, let's welcome Alán.
Thank you very much. Thank you. This is my first time in Hong Kong, and I'm very happy to be here. So thank you for everybody that is here. So let me tell you a little bit about the topic I've been thinking about for the last maybe 7 years, which is self-driving laboratories, which I'll tell you about. So what is the big problem I'm trying to solve? If you imagine how long it takes to commercialize a material, since it has been discovered all the way down to mass market, it's about 25 years. Name one. Lithium-ion battery, 25 years. Solar cell, 25 years. OLED, 20 years, right? Gallium phosphide, or gallium indium phosphide, electronics, et cetera, et cetera, et cetera. I don't know, you can keep going, thinking about which material has been discovered and all the way to commercialization. You have to think about why, of course, physicists, chemists, material scientists, chemical engineers, industrial chemists are all involved, but we pass things to each other in a very disorganized way, okay? So I've been very interested in how to accelerate this process. So I'll give you one example, and I'm gonna start with bird poop, okay? So you probably you know that before the nitrogen fixation catalyst, a lot of the fertilizer was basically bird poop, okay? Basically it comes from Chile, and it was taken in the boats to all over the world, okay? And this is amazing, okay? Also 20 years, but back in 1892, Bosch and Haber did the nitrogen fixation process, and they were systematically searching 50 to 100 materials a week, just remember that. They did a high throughput screen of 20,000 materials, and they found the Haber-Bosch catalyst. Okay, how many of you have seen Avengers Endgame, the movie? Avengers Endgame. You know which movie I'm talking about? Raise your hand. I ask many questions, and I ask people to raise their hand. So about half of you, which is about right, because in the Endgame movie, at the end, half of humanity dies. Remember that? So this is basically what would have happened if we didn't have just that single material. Because the carrying capacity of the human food carrying capacity is half the current world population. Perhaps that is the most important material we have discovered, right? So that's an example of why materials are important in society. But notice how even Haber and Bosch used a high throughput screening process to actually discover the material, which is very interesting. Another topic close to my heart today, I'll be telling you about organic emitters, is the organic light emitting diode. Okay, so the history starts with 1987. Tang discovers the OLED. How many of you have a cell phone with an OLED screen? Raise your hand. Okay, who doesn't have a cell phone? Okay, most of your cell phones have an OLED screen, okay? Actually, in Asia is where you use mostly OLED screen because it's very sunny, okay? They were commercialized in 2007, okay? And since then, I think everybody in the world, more or less, that has some money has a cell phone with an OLED screen. That's a very interesting thing. And the IP for the OLED screen is basically consolidated in the Universal Display Corporation out of the group of Stephen Forrest in Princeton. It's a $7.6 billion company, and it's usually a strong buy. So this is my stock market recommendation for you. You should buy stock in UDC. I don't own any, but you should. So now, we were just talking about high-throughput virtual screening. It's kind of the old way of doing things, and that's how I got into AI. At the time, Samsung came to me and told me, okay, Alán, here is a big grant. I want you to use high-throughput virtual screening to design OLED materials. So I started working on this paper. Now Rafa used to be in my group. He's now a professor in MIT. We started screening about 1 million molecules, a library of 1 million molecules. We used machine learning, one of my first machine learning papers. We screened, we trained the model with 100,000 quantum chemistry calculations and predicted the 900,000 remaining ones. So we shared a space of about 1 million OLED. About 30 or so, we made experiment and devices. And then 3 of them were good enough for a Nature Materials paper. Made Samsung happy, but it's not in your cell phone, so I am not driving a Tesla, okay? Still, it sucks, right? From 10 to the 6, I can only make 10 to the 1. This is when I was about to move from Harvard University to the University of Toronto. And I said, if I move to Toronto, I might as well build a lab because I want to automate chemistry, right? So I started thinking of this idea. Many other people also were thinking about it, but the idea is called self-driving labs, the same thing as a self-driving car. But instead of thinking about moving around in Hong Kong, and as you know, you can enter a GPS and say, take me to, I don't know, Kowloon, whatever, and then it will take you, right? Well, in chemical space, take me to a molecule that is good to be a battery or a molecule that is very good to be an OLED or whatever. So the difference between high throughput experimental screening and inverse design is that we're going to be doing very few experiments at a time, 10, 20, 50. Doesn't really matter how many experiments you're doing, but you update your Bayesian model of what the experiment space is, and then navigate using AI. Okay, that's what we're trying to do. So for that, you need robotics because you need to automate the lab, and you also need AI, and a lot of software, actually. So before that, I'm going to tell you a paper that I wrote about 5 years ago that is kind of like a perspective of how theoretical chemistry should look in the 21st century. And because I have a lot of theoretical chemistry colleagues here, I'm going to talk about the 20th century theoretical chemistry and what I like to call the 21st century theoretical chemistry. Okay? So first of all, simulation. This is a book from my former colleague at Harvard, Peter Gallison, historian of science. He says, the world is bound to simulation. I flew today on a plane, or 2 days ago on a plane that was simulated. The chip on my laptop is simulated. Everything in the world right now, engineering-wise and materials-wise, is simulated. Without simulation, we don't have the current reality. Okay? So computer simulation is very important. And what is computer simulation for the 20th century? I would like to say that, first of all, the field of quantum chemistry. Raise your hand if you're a quantum chemist or a quantum physicist or a theoretical material scientist. Okay, friends. Well, even computational drug discovery is okay as well. Okay? Quantum chemistry is at the birth of 4 different fields: computer science, physics, chemistry, and applied mathematics. And this book called Neither Physics Nor Chemistry, sorry for the graphic looks bad, is a good book to read about the history of the birth of the field. It's a field that comes from those 4. Okay? And this is one of my favorite quotes of all time. This is actually Samuel F. Boyce. Sorry, I forgot to put the name. Samuel F. Boyce, which is the advisor of the advisor of the advisor of my advisor. So it's my great advisor, okay? And he should have gotten the Nobel Prize, and not his student, Popple, because he was the first one to run a quantum chemistry calculation on a computer, okay? On a modern computer in 1955. And you can read the quote here. He says, here enters a chemical question, and then the story says he took out the printout of that computer program in the Quantum Mechanics Conference of Boulder, Colorado, took out the printout and said, here enters a chemical question, here comes out a chemical answer. Meaning structure to property. Okay? Here's Levin. Levin, 1957, he says, the most important role of quantum chemistry is to find molecules useful to society. Okay? Okay? Molecule before it has been synthesized in the laboratories. So the great grandfathers of quantum chemistry are already talking about what I'm going to tell you about. You can read this quote a little bit about machine learning now. Ask a chemical question on one end and produce an answer on the other. How many of you have used ChatGPT? I don't know if you can use ChatGPT here. I don't know, but okay, ChatGPT. Okay, and then you can see here the other thing, important molecules for society. How many of you are thinking about catalysts, batteries, etc.? Molecules that are important to society, drugs, right? Okay. So the only problem with theoretical chemistry of the last century is that we know everything about it. I have to say, we know a lot. Okay, look at this. This is 1957. If you do theoretical chemistry today, I bet you some of you are working on a lot of these different things. Non-adiabatic effects, right? New faster integrals, new density functionals, right? That's kind of theoretical chemistry of the 20th century. Okay? So this is what I wrote in that paper with Roland Lead and Markus Reicher as what I think is theoretical chemistry of the last century. Okay? Given a periodic or molecular structure, obtain its energy or other properties in the gas phase or a solvent model efficiently on a digital computer. Do you agree with that definition? Theoretical chemists, computational chemists, material scientists, molecular dynamics, quantum chemistry, DFT, etc. Right? So what is the 21st century chemistry? Right? What is it? It should be something different. Of course, we continue doing that and respect that, but we build on top of it, like in the shoulder of giants. We need to do new things. Okay? So what is the message of the new things? So in the paper, I wrote that these are the drivers of technology in the 21st century. Computing everywhere. Who has a cloud account of any type? Who stores their photos on the cloud? Who has WeChat here? You know, Internet of Things. Who has some device in their house that is connected to the internet? Absolutely everybody. There's more devices connected to the internet than people in the world now. I don't know if you guys know that. That's incredible, right? So anyway, these are the drivers. So I argue theoretical chemistry of the 21st century should take advantage of these drivers, and these are the three that I added. These are the ones from the World Economic Forum, and these are the three that I added that are very important, like CRISPR, quantum computing, right? And very important digitalization of matter I'll be telling you about today. Okay, so what are the challenges for theoretical chemistry? I'm going to talk about 6 challenges. I believe these are the 6 things that we theoretical chemists should be working on this century. And of course, you can have your 7, your 8, your 9. These are the 6 I like. So don't be offended if the ones I'm showing you are not the ones you care about. This is my opinion. Everybody has an opinion. But anyway, my opinion is that this is the 21st century theoretical chemistry. When faced with any complex chemical question in natural language, okay, it could be, I don't know, Spanish or Cantonese or whatever, the computer should be able to show you the answer. Again, in natural language or in virtual reality or whatever. Okay? But you don't it's going to do a lot of AI calculations in the back, but it should be like a natural language interface. I think that is what we need to aim for. And this was written 5 years ago before ChatGPT. So now these are the 6 challenges. The designer challenge. So in the last century, we went through structure to property. In this century, we have to go from property to structure. And there are models, as I'll show you, that can go directly from property to structure to do what is called inverse design. So that's number 1. Number 2, okay, let's talk about the challenge, and then I'll show you more challenges, okay? So we were just talking about this paper. This is now my third most cited paper. In this paper, we actually built what is called an autoencoder, okay? It's a very strange machine learning model because it sounds very stupid. It goes from a molecule to a vector space called latent space and back to the molecule. So you spend a lot of computer time to train something that if you give it benzene, it will give you benzene back. So you may say, Alán, that's pretty stupid, right? Why would you make a model that just gives you back the same molecule? Well, because it's actually taking a discrete space into a continuous differentiable space and back. That means it solves the chemical space mapping problem. I can map chemical space reversibly. So I can go into this weird space called latent space, design something, and come back. And the way I do that usually is I have another model that lets me climb a property. And once I get to the high of that property, I can go back to the latent space and figure out what is the molecule I'm designing. Raise your hand if you have done any inverse design. There must be some people here are doing autoencoders. Not yet? Okay. So it's very cool. So it doesn't really matter what generative model you're using. Even the Monte Carlo method and molecular dynamics are generative models. They are generative models of the Boltzmann distribution. Okay? So if you're running molecular dynamics, you are already using a generative model. Right? Generative models are very interesting nowadays. You can generate text, you can generate images, you can generate whatever. Right? But we are care about molecules, and we were one of the first groups, if not actually the first group, to use generative models for chemistry. Okay? But since then, we have used GANs, genetic algorithms, and of course, language models. Here are 2 papers on language models. Okay? And also, etc. It doesn't matter what you use necessarily. What is most important is the data, then the representation, and then the model. So the model, you can interchange the model. It's going to be the least important thing. The most important thing is always the data and then representation. So I'll tell you a little bit about those two. So now, I wanted to show you this slide because this is a collaboration with a Hong Kong-based company in Silicon Medicine. How many of you know in Silicon Medicine? Raise your hand if you know in Silicon Medicine. So I collaborate with my friend Alex Shaborankov and a bunch of people there. And this is the first paper where he used a generative model to design a drug candidate. So we are now in 2019, right? Sounds like ancient history. But back then, in 45 days or so, we took a generative model. You can see it's an autoencoder like mine. Generated some key compounds, did some filtering, tested it in rats. Now, 4 years later, every major drug company in the world has an AI program, for sure. And there's hundreds of drugs in the pipeline already, AI generated. Okay? So we got these 10 breakthrough technologies of 2020 for this work. Okay, so again, I'm in Hong Kong, so I have to show, and tomorrow I'll be with Levitt. So Levitt is a co-author of this paper. So with Levitt and Shaborankov and myself, we now used their tool, Pandaomics, also AlphaFold, and now this generative model, in 30 days to find a drug candidate for cancer. Now, it's so common to do this that we got in chemical science. We didn't go in science or nature. We just got now in chemical science. Okay? Just to give you an idea how it was not that exciting for science or nature. They said, whatever, this is normal. Right? So that's cool, right? It's kind of normal now to design a drug candidate in 30 days. So I really hope this changes healthcare. Of course, we need to change a lot of stages of drug discovery. Right? We need to think about process chemistry. We need to think about formulation. We need to think about et cetera, right? To really clinical trials. So AI has to enter all the stages of drug discovery. So I am now very interested in delivery. I'm very interested now in formulation of injectables, formulation of lipid nanoparticles, formulation of pills, et cetera. Okay? So my collaborator, Christina Len, and I have 4 years of work on this. So if you're interested in this topic, check it out. We use neural networks to actually formulate drug discovery. And a lot of the work is still unpublished, so stay tuned. Really cool stuff that we have done with Christina Len in Toronto. Now, you can also do solid-state materials. How many of you do solid-state materials? Raise your hand. Well, this is an example of an autoencoder that I really liked from my group 3 years ago or 2 years ago. We actually did a MOF autoencoder, so we encode and decode periodic MOFs. This is hard because it's kind of like a molecule, but also like a solid. So it took a lot of time to actually build this paper. Okay, so representations. What is a molecule? It is in the eye of the beholder. It depends. Ultimately, a molecule is a full wave functioning, multi-dimensional object, right? An infinite basis set. Doesn't fit in a classical computer. You have to use a quantum computer to use it, to think about it. That's the ultimate representation. Obviously, you can use electron density, molecular orbitals, right? You can also think about it in terms of strings. You can think about it in terms of graphs, in terms of bag of bonds, or in terms of geometries. I told you the most important thing is data. The second most important thing is representation. You have to think about what is the best representation for your molecule. So I'll tell you an advance from my group on text representation. This is called smiles. Sorry, selfies. I'll tell you first about smiles. Okay, raise your hand if you know what smiles is. Okay, it's a text-based representation. Okay, raise your hand again. You should not use smiles ever again. It's obsolete, deprecated. You should not use it. You have to use selfies. I'll tell you why. So SMILES is great. It's a text representation. You know which molecule is this? Does anybody know which molecule is this? It's illegal here. It's MDMA. Okay, so I like to put drugs in my papers. Okay, so this is MDMA. Okay, so ecstasies, right? So you put ecstasies and you actually look at how ecstasies is written. If I forget a parenthesis, if I change this double sign by a triple sign or whatever, I'm gonna get a bug. A SMILE string is a program for a molecule. Okay, it's a program of how to draw a molecule. So the question is, can I have a program that no matter how much I shuffle it, the program is exact, right? All of them give you a valid molecule. Turns out, postdoc in my group, Mario Kren, figured out how to do this with a rule table and symbols. The true idea is that you can have symbols that represent sometimes numbers and sometimes branching, for example. So the symbols can have different meanings depending on their context. So in other words, when you represent a molecule with a selfies, no matter how much you shuffle the string will always be a valid molecule. This is amazing performance gain for machine learning. And we have a Python library. You can just download it, and then you can convert your selfies to SMILES to selfies and forget about forever and ever for boring SMILES. Okay? Basically, this does the same, except organometallic. There's a lot of problems. We cannot do organometallic complexes. But how important this is an autoencoder. This is the density of molecules, 2 orders of magnitude gain. No matter how much this means, I'm not going to spend too much time telling you this. Same thing about an order of magnitude better generation in GANs. I'm not going to spend technical details here. I know this is a very varied audience. I'm trying to convince you it works. Now, in this paper last year, we show that only selfies can generate molecules of this size, atom by atom. We just put a paper on the archive. I have to update this. For antibody drug conjugates, we can do full protein with drug conjugates, atom by atom, with AI, generating them. If you use SMILES, the errors accumulate, and the SMILES just doesn't work. So if you really want to generate atom by atom a molecule as big as this, the only thing that works, selfies. Okay, and then just this year, with my student Austin, we actually now are doing group selfies. Of course, you can imagine that you can simplify a big selfie string by adding groups, which, if you look at the paper, allows you to actually think more like a chemist. You add certain groups to your system, and now, if you define the groups correctly, then it's more like a medicinal chemist. You can imagine having a very small string with all your reagents, and then as you shuffle the selfie strings, you will get reasonable molecules. So group selfies is a different library, but it also works very well. We show in the paper it's much better. Okay, so that's the story about generative models. Now, it's great, you can generate molecules, sometimes you can make them a drug, but how can we make sure experiments are faster? How many of you are experimentalists? Raise your hand. So if you're experimentalists, right, you have a HUD per student, and this experiment take a month, right, or 6 months or something, pretty. When we work with Li Chuan, for example, right? How long does it take to make a molecule? 3 months, right? So Li Chuan made me do this work, right? I was working with him and I said, too slow, okay? Li Chuan was too slow, okay? So in 2018, I wrote this paper. I said, this is theoretical chemistry of the 21st century. It's the same paper I told you about. Organa, because I was thinking of Cortana at the time. Organa, I want to make an OLED. These are the properties I want about the OLED. You can read yourself quickly, right? And says, okay, these are the 50 compounds. I want to make 30. I need the symptoms, order on the internet, the reagents, send them to me, etc. Okay? Okay, do you want to see the augmented reality? I thought augmented reality was going to be more interesting at the time. This is the thing I just didn't get correctly. My pleasure, Jane. And then blah, blah, blah. Okay? So there's a couple other ones, like the chemical Turing test. Can you, and this is very important related to ChatGPT, can I ask a computer a chemistry question and get a chemistry answer? Replacing a student, then replacing a professor, right? One day our job maybe will go away, and then we can just, I don't know, have fun in the beach or something, right? But the most important thing is, how does a computer learn, okay? So those are some of the questions I put there. I'm going to skip this, okay? Well, I'm going to tell them all to you. Feynman test is a quantum computers. Quantum computers probably are the only thing that can do exact simulation of chemistry. If we have an exact simulator of chemistry, then we don't need a lot of DFT, for example. We will kill DFT. So these are the kind of questions that I think the 21st century should be working on. This is augmented reality. Can we feel a molecule? Can we understand a molecule, right? I think those are the important things for theoretical chemistry. Now, I'm going to spend time for the rest of the talk on one of them called the matter computer. It's inspired by Lebdin. Raise your hand if you're a computational person. Can you imagine controlling experiments as if they were a GPU? That was our dream, right? I want to have APIs that control a chemical experiment as if it was a GPU. And I call it the matter computer, and my friend Lee Cronin calls it the chemputer. Okay, a chemistry computer. It's a machine that does chemistry. Now they're called self-driving labs. But let's go about the history of self-driving labs. I like to talk about history always. So what was one of the first automation in chemistry papers? Here is a paper to synthesize peptides automatically. Okay? So you put the peptides in these cartridges. You use actually rollers, drum programmers like punch cards. You put the punch card, and the punch card has the peptide. You know? Lysine, alanine, whatever. And it comes out a peptide. This is the reason why biology is here and chemistry is here in automation. Biologists can make peptides, sugar molecules. They can make DNA, RNA in a machine. We, the chemists, cannot make a molecule in a machine yet, as CC, as a biologist. Okay? That gave this chemist the 1984 Nobel Prize. This is called Bruce Merrifield. He got the Nobel Prize for this machine. Okay? So now, what is the first closed-loop self-driving laboratory paper I could find? If you find an older one, I will give you $100. I'll mail you a check. 1,000 Hong Kong dollars, if you want. I'll translate it to about 1,000, okay? So this is the paper, 1978. I was 2 years old. He was 5 years old, okay? Programmed in BASIC in a PDP-11 computer, okay? And it was at the SK of GSK, so it was used for process chemistry, okay? Isn't that cool? First self-driving lab. So a lot of the good ideas come 10, 20, 40 years ago. Okay? Okay, so for doing a self-driving lab, you have to do now a completely different form of theoretical chemistry. You have to build this control software that does AI and controls the machines. So if you come to my lab today, you visit, that's the thing we're doing. We're not doing DFT anymore. We use it, but we are programming these kind of things. Right? So these are the different types of way of searching chemical space. High throughput experimentation is like shooting randomly in space. It's very inefficient. It's almost doing experiments in random or in a grid. Okay? Chemical space is very high dimensional. It's 10 to the 82. You throw a grid in chemical space, you're going to be lost, usually. Right? Generative models are fantastic. I showed you we have generated drugs with it. The problem is that they generate molecules that are very hard to synthesize, or molecules that might be a little bit crazy. So we advocate for a closed-loop approach where you only search synthesizable molecules. And works for certain applications, I'll show you. So in this paper, about 4 years ago, we published the different areas that you need to work on. And I think I have grad students working in all of these areas. Right? So these are areas that you need to build a self-driving lab. Okay? Okay, so now let's talk about my application. How much time do I have left? Half an hour? How long is the talk?
It's usually 45 minutes.
Perfect. So I have 15 minutes. It's okay. My talk is way long, but I'm going to end in 15 minutes, okay? No problem. Organic lasers. So how many of you know of Hendrik Schon? Raise your hand. No? Oh, he knows Hendrik Schon. Great. He's the most interesting fraudster in chemistry. Okay? This guy, basically, one of the biggest frauds. When he was at Bell Labs, he had amazing organic semiconductors, organic superconductors, organic lasers. Okay? All bullshit. Fabricating data. He was a very good generative model of artificial experimental data. Okay? So one of the people that was fooled, he says, Stephen Forrest at Princeton University said there, look, Stephen Forrest. He had a very genius postdoc. How many of you knew Chihaya? Chihaya? incredible guy, right? Did you like Chihaya? You like him? He's amazing. This guy, I want to just hug him here, take a photo now, and I hug this guy. He's amazing. My friend Chihaya Dachi, about 7 years ago, I told him, I want to use robots for chemistry. And Chihaya told me, do organic laser. I have only 10 molecules synthesized, published so far. Very hard to make the molecules, and very hard to think about how to make an organic semiconductor laser. That means like your OLED from your cell phone, but emitting coherent light inside of a cavity. I said, okay, let's do it. Bring it on. Why will be super cool? Because certain colors do not exist in inorganic. Actually, there's places in inorganic compounds where you cannot emit very well, green, yellow. And also it could be flexible. So just imagine all the technology that could be lasers. The most interesting will be augmented reality glasses because they could emit light to your eye directionally. Right? So you could see, I don't know, all sorts of things with your glasses. Okay, so what do you need? You need to minimize the excited state. And who is a physical chemistry here? This is my physical chemistry slide. Minimize the absorption and emission spectra, minimize the excited state lifetime, and intersystem crossing. So it's all Jablonski diagrams. You have to minimize certain rates and maximize other rates. You want to be able that the molecule does not have all of these crappy processes. You don't want the excited state to absorb. You don't want to send into the triplets. Like the OLED. In the OLED, you like to be there. You like to be able to pass between the triplet and the singlet. Here, you don't want that. You want the molecule to be almost like an atom in some sense, absorbing and emitting light really quickly. And have a huge oscillator strength. So we started working on that with these crazy guys, Martin Lee, Bartosz, and Jason Hein, in a very large DARPA project called Madness. Okay? So the DARPA project was 5 years ago, just ended, so I'm going to show you the results. Okay? First of all, we are mimicking biology. What do you do in biology? In biology, you use chemical blocks, right? So we take the chemical blocks and combine them in a way that we have the reagents in our computer and do carbon-carbon coupling reactions to generate a chemical space. Okay? So we can do sequential synthesis to actually make something that looks like DNA or RNA, right? And in the case of organic laser, this works because the molecules usually have a cap, a bridge, and a core, a little bit like a spaceship from Star Wars. Okay? So that's why we are building spaceships from Star Wars, to make them lasers. So this is the lab I built in Toronto. I have many other collaborations and labs around the world that we work with, but we have a synthesizer, we have an HPLC, and we have a laser. I like to say this is a physical chemistry lab, analytical chemistry lab, and organic chemistry lab controlled by a theoretical chemist. That is real madness, right? This is how it looks, my room. So you have here the synthesizer, the HPLC, and the laser table. And when you make a molecule, it goes through all the system, and in about a weekend, we can do 40 molecules. We can get their optical characterization and after the synthesis. And I'll show you our Hello World example that was published January this year, and then I'll show you the final example. These are some of the details of the system. All of it is automated, controllable by Python, and we have published a lot of the tools in open source, so you can build your own here in Hong Kong. Okay? So this was our first Hello World paper. We wanted an experiment that you could do on a weekend that had simple chemistry, one step. Okay? Simple. Suzuki coupling, core, and bridges. So we had these caps, and we had these cores. Again, the idea was to show that we can do this on a weekend. So we just throw our reactor, run the whole system. We actually left it do it by itself. Okay? And it was just published in Advanced Materials this year. How does it look like? Let me see the video. Shit. Okay, so this is my automatic power dispenser. This is the most expensive salt and pepper shaker of the world. It's about a $250,000 machine that shakes the salt and pepper and weights our catalysts to a very, very high precision. Okay, so that's kind of like a very nice machine. If you want to weigh powders, I recommend you to buy this Quantus machine. Okay. Then our reactor, sorry, the internet is a little bit slow because I have a VPN, I guess, and stuff. So I didn't test the animations. Let's see if it works. Yeah, so this is the synthesizer. These are the arms that open and close the reactors, dispense powders and liquids, and so on. Some of you probably have seen these machines. These are machines since the 90s, right, for catalyst screening, but now we're using them controlled by AI, which is what is new. All of the software here, all of this is controlled by AI, and we optimize many different things like liquid dispensing parameters and a lot of things like that. And finally, I want to show you our home-built machine. We just submitted to Nature Protocols a $5,000 machine. This is homemade. So if you want to make flow batteries, you want to make something like this, you can actually build a machine like this, and this can do 2-step Suzuki coupling, so you can do all the reactions, right? This is homemade, and this is kind of how we're thinking. We're going to make machines that are quite small. They're about this size, and you can just build it. So we submitted the protocol. If anybody wants a preprint, I can send it to you. You can build your own. $5,000. Okay? You can see here the 2 steps of the Suzuki coupling happening. You know, the molecule is already a laser there, actually. So 95% of all the molecules I did for this project were made with a $5,000 machine, not with a $1 million machine. It's easier than the ChemSpeed. So now, remember the Hello World paper? 40 molecules? Let me tell you what this is. This is the optical gain. This is a figure of merit for an organic laser. It basically means what is the probability that a molecule that absorbs a photon gives it back to you. So a laser is very good at giving you a photon back. Okay? Higher the better. And this is the color. There's some Pareto here. This is Chihaya's best molecule. This is our first experiment. So Chihaya had made 10 molecules. We made 40 in a weekend. And just by chance, by thinking about the chemical space correctly, my postdocs and I basically made these molecules that are better than Chihaya's. Here is the threshold energy. This is when it becomes a laser. This is the device. You can see the narrowing of the emission line. And this is our top molecule. Okay, so this is experiment done by Chihaya. Chihaya is also a collaborator. So we send Chihaya the white powders, and then he makes the devices. Okay? So now, in the remaining part of my talk, let me tell you how we do it across the world. We just put a paper on the archive that we submitted to a fancy journal. We just put it on the archive about 3 weeks ago or something, so you can read this paper. So the sun never sets in our empire. We make molecules here. We make molecules in Toronto, Urbana-Champaign. We do experiments in British Columbia and in Glasgow. We have calculations in Korea and Poland. And we make devices in Japan. 7 labs. Okay, all controlled by software. So we call it a global self-driving lab. Okay? So we have a software that knows where are we making in different labs around the world, where are we testing, where is the shipping, and that's how we do it. So we control it all by software. Okay? So we use asynchronous Bayesian optimization. Basically, we optimize the prior of the problem by having an experimental database of the molecules with all the properties. And every experiment that comes back asynchronously, we update the machine learning model. And we continue predicting what's going to be the next molecule to make. Pam, pam, pam. We iterate like that. Now, this is hard. This took us 5 years. This paper took us 5 years to do. So I told you about the 20 years. OK, building a self-driving lab now takes 5 years. We have to reduce the time to build a self-driving lab. There's a lot of technology that we are developing as we build them. Okay, so this is the chemistry that we actually use. We use this boropene and borotida coupling by Marty Burke, and we very carefully optimize the synthetic reaction so that this couples to this first and then to this. Single pot chemistry. So I'm going to skip the details about that, but on the side we got a science paper by using AI and optimizing the reaction conditions for Suzuki in general, which allowed us now to do Suzuki 50% more efficient for any Suzuki reaction. So this is another very important aspect of machine learning. Now you can optimize the yield of generic chemical reactions. This was about a 6-month project. It was about 100 reactions or so that we ran, not that many, but with AI, more than 100 reactions, but with AI, 4 different rounds what allowed us to actually do this. How much time do we have left? Like only 10 minutes?
Yeah.
Well, okay, no worries, guys. I just want to make sure I don't screw up. Now, the other important thing, and Li Chuang also knows about this, is you want to know the kinetics of everything, right? So this is where my friend Jason Hine is a genius. He actually has analytical chemistry coupled to his robot, so that whenever we're trying to figure out what happens with a Suzuki reaction, we know when to stop. Because when you're cooking, okay, it's Chinese cooking. I was going to make a joke about a paella, but the same thing happens in Chinese cooking. You're with a wok like this. What happens if you do it too long? It just smokes, right? It becomes shit, right? Same thing happens with any cooking. This is an example. If you stop the reaction here, everything is nice. But if you continue like this, you have having side products. So we also look at our Suzuki couplings with this type of robot to find out what are the reaction conditions, when to stop our reactions. And Marty Burke has been shortening the time it takes to do a Suzuki coupling. I cannot tell you because he submitted the paper to a fancy journal. But I can tell you it's about an order of magnitude faster, even 2 faster than regular Suzuki now. with AI and things like that, right? An important reaction design. So these are all the reaction conditions that we use. These are the AI reaction conditions. This is another set of reaction conditions. And by using AI reaction conditions, we increase the product formation by a factor of 2. Okay? So now, this is the number of molecules that we did. We did about 1,000 or so molecules, 500 in 3 months. Okay? By doing this now, we can actually generate molecules and test their laser properties, about 50, 40 a day if you want. Okay? Many times the machine breaks. Sometimes we don't have chemicals, etc. So our rate is way lower than if we were running 24/7. Our HPLC gets clogged, it fails. You know, always things are failing. I'm not going to tell you the robot works all the time. Most of the time, my postdocs, they told me I'm a plumbers fixing this. But when it works fantastically. Okay? So we were able to actually run the organic lasers, and I'm going to show you how they look like. Sorry, this sucks because the video. I know. This is the control software. Okay? And maybe I will skip it, but this is the software that decides where to ship the white powders around the world. Okay? So it might be very slow, but you can see which molecule it is, and you can see which lab was which reagent, and we send reagents to another person. We just put this paper for this on the archive as well. Okay? So you guys can download the code to do this, and you can see which lab, which fragments, and so on. This is the only way we can do is we have to have a database for all the molecules that we have all around the world. Right? And you can think about how many experiments were used just to actually start. And we now know how many get full optical characterization, how many have low yield. So it's about half of them that we can measure at the end. Because some of the molecules we make either are insoluble or don't have good laser characteristics. So after the whole process, it's about half of them that we can measure. Okay? So now, when we sampled the hypercube, we found very good molecules. This is kind of like a sampling of the space to train the machine learning model. I'm really going fast because I'm losing time. I'm worried, right? But then we use the Bayesian optimization, and for that we have a lot of papers where we actually developing algorithms to actually optimize in chemical space. I encourage you to look at these papers. These are the papers that we use to actually optimize what is the next molecule to make. So there's many grad students in my group that are doing Bayesian optimization. Okay? I'm going to skip this. So what do we do? Now we do DFT. We do 170,000 DFT calculations. And remember those embedding vectors or latent spaces? We create an embedding vector that reproduces the DFT calculations. Okay? And we use something called ranking-based Bayesian optimization. You can have the details in our preprint to actually map that to a Gaussian process to design the molecule. So there's a lot of machine learning technology we had to develop. But this is a cool thing. This is a hypercube sampling. And this is when we started optimizing. When we got here, we ran out of time. The DARPA project ended, ran out of money, ran out of patience, and ran out of reagents. We lost our most important bridge block. So I told the group, stop. That was about August. Stop, write a paper, I'm done. This is 5 years of work, right? This is when we were optimizing the reaction conditions. This is when we did the hypercube. And this is when we base up about 1,000 experiments. So said, okay, enough for a paper. Okay? So you can see here all our molecules. There's a Pareto front here. Chihaya's molecule is around here. So we have about 35 good molecules above Chihaya's molecule. These are our top 3 molecules. And you can see here the laser performance and very low threshold energy. Okay? So just to show you, these are real molecules in a device. They work, etc. Right? Now, I'm a theoretician, so I can calculate with certain assumptions what is the upper bound. How good an organic laser can be. You can read in the paper, there's some assumptions about the language of a molecule, emission lifetimes, etc. We believe that the maximum gain cross-section will be like this, and the maximum gain cross-section as a function of wavelength in the log scale looks like this. So these are our molecules. We're about 1 or 2 orders of magnitude where we can improve over the possible. So if you were to continue optimizing and expanding the chemical space to more reaction fragments, to more interesting devices, maybe we will be able to get close to the theoretical optimum. Obviously, there's other mechanisms like degradation, solid-state mechanisms. We might not be able to ever get to the maximum, but I think our paper is the first paper that shows actually what is a reasonable maximum for an organic laser. Right? How far you can go. Okay? And now, let me just show you a nice video. This is how they look. So this is your reactor, you shine a laser, and this is how it looks. So those are perhaps the brightest molecules in the world. So I think this is the moment to end, just telling you what we're doing in Canada and maybe inspire my colleagues at Hong Kong. So recently we received the largest grant ever given in Canadian history to a university. We got $150 million to build a self-driving lab. Okay, self-driving labs for a lot of professors, not only for me, but I don't have time to show you, but we're doing robots that actually do chemistry like this. They use computer vision and they, okay? I use a lot of time in my talk, otherwise I'll show you that. We're building a building. This is a building that will open in 2026. Right now we have our self-driving labs all around campus, but this is an extension around our university that will have all the rooms full of self-driving labs. And we have self-driving labs for inorganic materials, organic molecules, polymers, hybrid, biocompatibility, scale-up. And because this is a consortium, I invite professors in Hong Kong to be part of the consortium, to collaborate, to come and visit, etc. So it's many professors that are there. Last thing I will say for the postdocs in the room, or for people that want to move to Canada, we are hiring 12 professors in this area. So if you do AI for materials, you're doing synthesis, we're going to be hiring senior and junior. Okay, so it's a little bit colder than Hong Kong. Okay, okay. So I think I'm done, right? So I can keep going. So I'm going to stop here and actually thank you for your attention. Thank you very much.
Thank you, Alan, for the fantastic talk. Now, let's just keep enjoying this scientific journey first. Any question from the audience?
Okay,
yes.
Thank you.
The question I want to ask first is, can you predict the device lifetime of the OLED emitter? Because for OLED and organic laser, for that matter, lifetime is the only thing that matters eventually.
100%. The answer is complicated.
Yeah.
What I want to do is a robot that makes devices. And we have published with Curtis Berlinger and Jason Hine a robot that can do HTL. So we can do whole transport layer optimization already. I have a paper in Science Advances. We have a robot. It makes HTL, and we contact it, right? So that's a good step, right? But in principle, what we need to do is the following. We take a molecule that comes out of our prediction, and now we're going to vary the experimental conditions to make the device. A little bit like Christoph Brabeck does for organic solar cells. I also have some papers with Christoph Brabeck. We use AI and optimize, the combination of, say, in that case, donor, acceptor, and additives. We did the first tetra component organic solar cell with Christoph Brabeck by optimizing with 4 components. That was in about 2020. I think that's what we need to do for OLED. Because, or an OPV, sorry, OLED and organic laser. If you make one device at a time and optimize by hand, AI cannot really help you. So ideally, you want to have a model that takes you all the way down from the molecule, all the way to the device. You probably don't have too much simulation data anymore. It will be more experimental Bayesian optimization. So I am thinking about how to robotize the devices.
I mean, there are software out there that can simulate the device performance based on the electronic or photophysical properties of a material.
Yes.
I wonder if you can combine these two, like material screening and the device simulation.
100%. I believe that device simulation could help us build a latent space for the optimizer in machine. The same way we did it. We did DFT to build a Bayesian space, but what happens is that simulation is here and experiment is here, and you have to have an AI model that connects the two. Okay? So yes, if I had another 5 years, maybe 5 years from now or 3 years from now, we hopefully have the entire platform, and we can also make OLED devices. So I am doing something similar in the space of flow batteries. The reason I didn't present it here is I put a patent that hasn't come out yet. That's why. But we use robots. We're trying to use robots to do electrochemistry. We're even polishing electrodes with a robot. So in the case of machine learning for electrochemistry, we're farther ahead, but that's the same thing. We want to make devices to actually build organic flow batteries, so OLED. So yeah, the frontier is going to be now the device.
Okay.
We showed already we can optimize the molecule. Now we need to optimize the device.
Thank you. I have another question.
Yes.
I used to be an organic chemist. Purification is always the pain in the ass. So it's cool you can do automated synthesis, but can you do automated purification? And purification is extremely important for all the materials and organic lasers.
I'm going to give you a hug. I don't have a slide to show you, but the way Jason Hine purifies our OLED molecule, our laser, he invented a patented dual temperature solubility machine. Okay, so it moves between two different points of temperature very slowly. So transfers liquid from the hot to the cold, from the cold to the hot. Okay, and he uses this cycling method to purify materials. That's an example, an automated way of doing purification. But the cool thing that you say is the following. We got our $150 million, and now we're going to have different labs. Guess what is the team of my organic lab with Sophie Rousseau? So I only have one of the 7 labs. Even though we got all the money, I can only control one of the 7 labs. Okay? And in that lab, our topic is separations. So filtration, precipitation, because we know the only way we can really automate chemistry to go beyond 2-step, 1-pot synthesis is to tackle the separation problem since the very beginning. So we're building flow reactors, batch reactors, but also a bunch of rotababs and a bunch of different things to automate that. So the goal will be to have, say, the 50 to 100 more common organic reactions in multi-step, all automated. But that will take us maybe 7 years.
Okay, thank you. Just curious, in the paper you collaborated with Professor Adachi, so all the purification was done by human, right?
The way we do the purification, no. Okay, the way we purify in my robot, we use a semi-prep HPLC to do the laser characterization. So for that, we can just get...
Oh, sure.
We do solvent exchange, and in solution, we do laser characterization.
But for the materials that eventually use for the device...
When we send to Japan, we use the purifier. I'm going to turn this off. Okay, we use a purifier that Jason has. I'm happy to send you the paper. Okay. Actually, in our preprint, there's a description of how we purify. Again, it's 2 different baths at slightly robotic controlled temperatures and a pump that pumps back and forth. So yes, we automated the purification step, and we optimized the parameters of how to purify. Okay, so yes, the devices that we sent were purified with that simple technique.
Thank you. I'll definitely check it out. Thank you.
Yeah, I'm happy to. If you send me an email, I'm very happy to, of course, send you information, whatever you need. We are an open book, so we'll send you guys whatever you need to the device. But the professor that does that is Jason Hine in British Columbia. So he is the guy that knows how to purify. I'm just a theoretical chemist learning organic chemistry. Okay. Right. Whoever wants to go first. I mean, maybe him and then him.
Thank you, Professor.
Okay, then him. Okay.
Yeah. So thank you for your talk. I have so many questions, but the first is, what about the automated synthesis of inorganic materials, especially for catalysts for the electrochemistry? Have you had any project or any similar?
Yes. So we started building a robot with the Natural Research Council to build oxides. Okay. But then I cannot collaborate with everything, etc. So the NRC continued doing it. There's a guy called Robert Black. And I also collaborated with Ted Sargent on a robotic inorganic oxide robot. So now Ted Sargent took the robot and the NRC, and we just did some theory on this. So there are robots that do this. Interesting problems. Again, an interesting problem that happens when you do automated electrochemistry, believe it or not, is electrodes. Yeah. So we're about to put a paper in the archive where we take a robot that takes the electrode and just scratches it and then brings it back, and we're doing machine learning to figure out how much time it takes to clean an electrode. So you can actually keep doing electrochemistry. So yes, there's some stuff that we're doing in electrochemistry, but I am not an expert in making oxides and things like that, so this is my collaborators. I am.
Yes.
Yeah.
They also got very big fund from the government for the automated synthesis of the catalyst. I'm not sure if you have any collaboration for that project with Robert Black and Jason Hattrick.
Yeah. It's the same project. We collaborate.
It's the same.
We collaborate with them. Yeah. Jason.
Okay.
We recruited Jason Hattrick Simpers to Toronto.
Okay.
Yeah.
So another question is, for example, based on the property, you are going to predict one molecule, right? from property to molecule. So imagine this molecule is not exist.
So we make it in the robot. That's the whole point of my talk.
So
did you listen to my talk? Anyway.
Yeah.
Okay.
So what is the point of retrosynthesis planning in this part?
In this case, we only search the synthesizable molecule, so we don't need retrosynthesis. We only search the space of the molecules my robot can make.
Okay.
Okay. Does that make sense? So I believe to search a space I can make. I don't believe in searching just randomly, because randomly, most of the molecules you won't be able to make.
So one last question. Have you done any feature importance on, like, for example, for organic materials, sometimes some features are most important features.
We have done that, but we're not using features here. We're using directional optimization on the latent space vector. So yes, you could use a linear model to do feature importance. So the answer is yes, we've done it in many projects. This one is not one of them that is done that easily. But yes, it's important.
Thank you.
Yeah, it's an important field. Yeah.
Okay, thank you. That's a very interesting talk. So,
no. Look, I'm gonna turn this off.
hello. Okay. So yeah, I know the previous two questions is more about the robotics part, but I'm a theoretical chemist also. So I want to ask more about the like computation, like the combination, like the AI model. What? Don't use hand. Sorry. Hello. Yeah. Okay. So my question is like, when you say I want to represent a molecule, like no.
Okay, raise your voice. It's okay.
Yeah. Okay, it's like when you talk about like the key part other than data is representation. I really agree with that point. But like the one interesting for chemical optimization is that like chemical molecules are discrete. It's like there's nothing in between methane and ethane. So you cannot have, like, even though we say I have a magical molecule that can solve every problem, but it has only 1.5 carbon. It doesn't make any sense. So when you try to, it's okay. When you try to linearize it or try to shrink it into a continuous space, that's good for a machine learning perspective. But does that have any effect on the chemical prediction? Because even though we try to make it continuous, it doesn't necessarily make the things easier, because say for like integer linear programming is much harder than linear programming. Although like it looks the same, but from the discrete like constraint, then everything becomes like a mess. And the key art of the chemistry is about that constraint. So how does that, like, can you share your view on that point?
No problem. Actually,
yes,
I think a very important mathematical A very important mathematical idea in machine learning is called relaxation. Okay, so in machine learning, you usually never optimize discrete things. We use functions like softmax that take discrete objects and make them smooth differentiable objects. This is the reason, the reason I think this is a solved problem. ChatGPT is text, and text is as discrete as molecules. There is no letter between A and B, okay? Or the Chinese characters, I don't know how many there are, 5,000 or whatever it is, maximum, or whatever it is, maybe more. But say you have 5,000 Chinese characters, there's no Chinese character in between these two characters, okay? Same thing. So in images, in the pixels, there's no pixel in between these two pixels. So I argue in machine learning, everything is discrete. And for everything, we use softmax. Okay? So for example, for optimizing catalysts, I want to optimize catalyst 1, catalyst 2, catalyst 3. My model is continuous, but obviously, he is, a certain phosphine, he's another phosphine. There's no phosphine in between them. It's okay. What the model does is the following. Say the model ends between these two phosphines, just right here. Because it's probabilistically sampling, if you run my model one time, it will give me him, one time it will give me him. and maybe other molecule around. Yeah, autoencoders are probabilistic, and when the models are not probabilistic, and you're sampling like that, usually it will just give you, with a certain probability one or certain probability the other. Sorry, you're catalyst now. I apologize. Yeah, my colleagues here, I made them catalyst today. Yeah.
Okay.
Yeah.
And another quick
Okay.
question is about what you are making, still about representation. What you are making is about molecules, and we have smiles, we have graphs, we have molecular graphs, we have all kinds of things. But when we talk about materials, there's also another important thing is about their face. It's like how we arrange the molecules. And is there any way, in the representation, that can help us, in that sense, not just on the molecular level, that we try to characterize atoms?
You're thinking organic devices? You're thinking like assembly or something like that? Or you're thinking solid materials?
Say organic materials, say we have polymers.
Yes, herringbone or polymers and things like that. Yes, absolutely. There are people that are thinking about that. Of course, first of all, you want to make the selfies periodic, and Connor Coley has a periodic smiles package. That's not so hard. Then you want to think about supramolecular. So for supramolecular, I think you need to generalize the graph convolution networks for solids, right? To detect features in the amorphous space. There is a paper by a guy now at Google, used to be at Harvard with Tim Kaxidas, Doush Kubuk, that simulates, I was in his thesis committee, so I know this paper. It was in PNAS with Tim Kaxidas and Doush Kubuk. They're simulating liquids, and they're trying to simulate, sorry, not liquids, excuse me, glasses. And they're trying to find out what is the glassy part and what is the non-glassy part. And if you're going to break a material, where is it going to break? This type of problems. And for that, they use machine learning representations and look at the molecular dynamics, and then they can actually look at different regions of the assemblage. Okay? So Sharon Glotzer also has some beautiful work on self-assembly. So I know more and more people that think about assembly are doing machine learning. So the same question to, I forget your name, colleague in the back, but he's asking more or less a similar question. He's asking, what about the device experimentally, or what about the device theoretically, you're asking me. Next frontier. Actually, how many people here are students and postdocs? Raise your hand. I think 80% of the time I get that question every seminar. Okay, many people ask me the same question. So if you're a postdoc and you start your research group, maybe this is a good thing to do. Okay, for you guys to start a new research group, how to do machine learning of exactly your question. But I think it's doable. You need to think about that paper by Dogush. You email me, I can send you the paper. That paper was only spheres, but you could generalize it to, say, pentasines or to whatever. Or donor acceptor materials or something like that. But we haven't done that yet. My group is only small. It's only 40 people. I cannot do everything, right? But there's people that should be doing this around the world for sure.
I see. Thank you.
Yeah, thank you.
Okay, that's a very interesting talk. So correct me if I'm wrong. And for those generative model, my understanding is the predicted things cannot go too far away from what they learned. So we cannot expect that it really gives you some very creative or innovative solutions here. So could you comment on this, like how to improve this part?
Very great question. So the question is, yes, data in, data out, and obviously extrapolation is very hard, right? One of the answers is tons of data, okay? So see what happens with language models. If you feed the entire internet to a language model, suddenly it really looks like it's going outside, right? You're asking it so many questions and it can go larger and larger. So what is called a foundational model is a model that has tons and tons and tons and tons of data, right? So we never have built an autoencoder with all the molecules in PubChem, which is 90 million, right? We have never made machines, models that are as big as that. So there is a company called Stability AI that I know is trying to make such very large models. So one answer is, of course, more data. Then Keisuke Fuji, I think is his name. No. Oh, I'm forgetting his name. And it's in Japan. Sorry, it's not Keisuke Fuji. Koji Tsuda. Okay, sorry. Poor Koji. If Koji is listening online, Koji, I forgot your name for a second, but I'm jet lagged. So Koji Tsuda in Japan has a paper I really like. Koji is very smart in this field, okay? So I really recommend everybody to look at Koji Tsuda's papers. So you can think of an amoeba, okay? So you have your data cloud, and you know amoebas, you know, there are these bacteria that keep moving around and start looking for food. Say you are the food, right? So I'm trying to move towards you, but I don't have data points, right? So I throw data points here. So I will run more quantum chemistry experiments and slowly start heading towards the direction that has the best answer. You are the best answer. Okay. So what I do is I expand my data towards the best answer. So you can imagine algorithms that are like a cloud in hyperspace, in molecular space. And if you know that you have uncertainty, you run more calculations in the uncertain region and keep optimizing that way. So I think that is the solution. But you also have to think about, Lee Cronin has algorithms for serendipity and creativity. So I also have a paper on creativity, how to think about digital creativity, how to ask the model to try to be as creative as possible. Now, in molecules, it sucks, because if you ask a model to look creative, just search my name and creativity. The molecules obviously come out really weird, right? Because if you ask a model to be creative in chemistry, it will do crazy organic chemistry, right? So you have to be very careful between creativity and reality. So somehow you need to make creative, realistic molecules. So all of you are identifying, I think, you, and you three, have identified 3 key frontiers. So thank you. That's really, thank you. The 3 of you, I think, have looked at three good questions of what are the next directions. But Koji Suda's paper, Tim Kaxida's paper, and for you, Christoph Brabeck. Yeah.
Maybe you want to generate one for crystals?
Okay. What about crystals?
So what about you were to do inorganic crystals or this type of stuff? So for example, you use different types of ions or even metal alloys that currently may be doing for catalysis.
Yeah. Of course, organic crystals is another frontier. There's people like Alex Tkachenko that do machine learning for organic crystals. He has done things like predicting what is the right polymorph of aspirin, right? So more and more there is machine learning for molecular crystals. I think I recommend you the papers of Alex Tkachenko. If somebody emails me, I will just send you the links to the papers to all these different questions of groups I know. So I think for you, the answer is Alex Tkachenko. Yeah.
He also visited here like 5 years ago.
Sorry? You did it yourself?
No, he also visited here.
Oh, Alex. Yeah, he's great. He was here. Okay, well, Alex Tkachenko is one of the foundation of AI for materials guys. He actually started it with Anatol von Lilienfeld, which you also recruited to Toronto. So.
Okay, very good. So maybe Huang Yong want to ask some organic chemistry. Maybe Suzuki, that's science paper.
Okay, it's an interesting way to optimize the Suzuki coupling. I'm an organic chemist. There have been a lot of papers, like in high-flying journals, on optimization using AI, right? But so those were like well-defined reactions, and I'm just wondering, what's the next step? For example, looking for like new transformations, because people have said that the organic chemistry is done, right? All the chemical transformation has been discovered, but I seriously doubt it. So how the machine can play a role in discovering unknown transformations?
So I have a favorite paper of that. So for you is Bartosz Grybowski, okay? So I'm trying to give a name to each one of you of the closest. I'm a machine learning algorithm that gives you the closest author in the literature, okay? So Bartosz has a Nature Synthesis paper that I am like this. He's also part of our DARPA project, but I am not part of it. This is what he said. He has the Cynthia software. If you know Cynthia, it's a software that has hard-coded, I think, 10,000 organic reactions, right? And he asked Cynthia, go and explore the chemical graph space and find iterative coupling reactions. So iterative coupling reaction is automatable, right? We always want reactions that you protect, deprotect, couple. Protect, deprotect, couple. Because that way, you make a robot that can, right? So in that paper, I think he identified 170 new coupling reactions. I am not enough organic chemist, but acid coupling followed by this and, hydrolysis, I don't know. So he basically searched all the spaces of the reactions in Cynthia for all the reactions that turned back onto themselves. Because to do a protect-deprotect cycle, you have to search the graph in such a way that once you deprotect, you have the same reagent. So he did it with 2 steps. He was also talking about with us about, well, why is it 2 steps? Why cannot do protect, deprotect, react? I mean, there's a lot of crazy things you can do, right? But right now he has a paper where he does react, protect, deprotect, for example. And he identified thousands, but he published, I think, in the supplementary information, 170. So our goal with him is to try to start automating them, right? Because these are never thought before iterative coupling schemes. So if you want to put the boronate and remove the boronate and so on, that's kind of like old chemistry. So to your point, and also Lee Cronin says this, can we run the robots to discover new reactions? You know, the Nobel Prize to Macmillan is a little bit like that, right? He was searching for photocatalysts with a robot, right? But he was not using AI, but he still got a Nobel Prize just by using random screening and his brain, right? The machine learning was Macmillan's brain and his students, probably his postdoc's brain, right? You were a postdoc of Macmillan, so his postdoc's brain, your brain. But the reason I'm saying that is, you know, really, I mean, what is machine learning is just a poor human's brain that is paid less than a graduate student, right? The human brain is still better. So maybe I don't know if this is the last question, but to end the talk, I'm going to give you a poem. Okay? This is a poem by the Argentinian novelist and poet Jorge Luis Borges. And this is a poem about chess. And he says, who is the god behind the god that moves the player, that moves the piece, that starts this game of dust and agonies? And the god behind the god is always going to be the human. So no matter how many robots we build, how many AIs we build them. So we are the god. So that's the point, right? So organic chemists will never lose their job. Theoretical chemists will never lose their job, etc., right? Because we always be building the AIs that will be doing the game, right? But I agree with you. Everything is in an infancy. You see, everybody is telling me the limitations. No new reactions. Suzuki is old. Molecules in solution. That sucks. How about the crystals, right? Sorry, how about the crystals? How about self-assembly? So the good news is the 21st century has a lot of things to work on.
Okay, sorry to ruin your end. I have another question.
No, let's begin again. I can give you more talk. You know, I can continue. Right? Just kidding.
So how far away are we from practical quantum computing for chemistry in general?
Very good question. How far away are we practical computing? So when I started the field in 2005, quantum computing for chemistry, and right now we can do about 20 qubits or something. You know, molecules. There's more molecules we can do or something in lithium hydride. I do think we kind of are reaching a problem. The problem is coherence times are not getting better. People are putting more qubits, but coherence times are not getting better. So it is very hard to answer your question because I'm not an experimental quantum computing guy. But the safe answer we've been giving for the last 5 years is in the next 5 years. Right? I don't know. I believe it's going to be in the next 5 to 10 years. It's going to be hard to overcome a lot of experimental limitations. But if you ask me, will there be 1,000 qubit quantum computer on the cloud when I started in 2005? I will tell you maybe never. So I am an optimist, but I don't have a date for you. My company, Zapata Computing, just announced it's going public, right? It's a big deal. But we shifted a lot from quantum computing to AI. Because we have our quantum computing group, but we think we cannot make too much more money in quantum computing. We make money, but to make a lot of money, AI can make more money. So even my own company accepts this, that it's going to take longer than next year. So if you're a public company, you want to make money, you kind of want to be in AI as well. So that's the reality. 5, 10 years, I don't know, you know.
So basically you're saying that quantum computing is limited by hardware at the moment.
The algorithms keep getting better and better and better. So I still have a quantum subgroup, about 15 people in my group. And we keep going down and down. The algorithms keep getting more and more sophisticated, right? So we just put a paper on differential equations and wavelets, and you can get exponential speed up here, polynomial speed up here. The algorithms look amazing. The problem is they require a lot of qubits and a lot of gates, especially gates. And because you don't have enough gates and you don't have error correction, then the algorithms are fantastic, but there's no hardware to run them on. So I'm starting to get a little bit bored because I keep doing algorithms and I cannot run. So, but I still work on it because we started the field in quantum chemistry, and I want to see the end. This is a long game for my whole life. Yeah.
Thank you.
Thank you. No, thank you. Your questions are amazing.
Okay, I think we have quite a fun time with Alan. So because this is his first adventure to Hong Kong,
Yeah.
so don't stress him very much. So he will come back again to chat with Professor Lin and Professor Huang. Okay, so also thank you all for coming here. So yeah, that's the end for today's event. Thank you very much.